This morning we will talk about, I will talk about the work of Martin Heirer on regularity structure. I mean, his theory of regularity structures, which is one of the achievements for which he got the Fields Medal last summer. And so the idea is simple, is that we want to do for PDEs what we've been able to do for ODEs with rough paths. So try to find some kind of structure which will achieve the same things. And there are, of course, a lot of difficulties in doing that. So I mean, just write it like this. We want to go from ODEs to PDEs. And then, of course, the application is going to be similar. Here we had basically SDEs. And now we want to, the main application is going to be SPDs, even though there's quite a lot of constructions which are purely deterministic. So I will start by giving some examples of the SPDs that this theory is able to give a notion of solution for. So one of the reasons why there was a lot of interest in this work is that there's quite a lot of stochastic PDEs which have been derived some decades ago by physicists, and which people were interested in, but up until the work of Martin Heirer, there was no notion of solution for this equation. So it was not clear what would be the right solution. But now, with the work of Martin Heirer, he developed a formalism in which we can solve these SPDs. So, okay, let me give some examples. First one is going to be the KPZ equation, which takes this form. So we have the function u of time and space. So space here is going to be one-dimensional. And just take the simple form, derivative squared plus psi. All right, okay, so let me just give us a quick definition of this object psi here, which is going to appear everywhere, which is white noise. So white noise is going to appear in all our equations. So white noise, it's a Gaussian, it's a random function. It's Gaussian, and it's given by the covariance. What we want it to be is when you take the product of psi at some point x times psi at some point y, basically, when x is different from y, they should be completely decorrelated. And when x is equal to 1, so it's a Dirac. So the covariance function is just the Dirac of x minus y. So this is just a formal expression, right? In fact, psi, when the object that we want to realize this, it's not regular enough so that this expression really makes sense. It's not a function, it's just a Schwartz distribution. So this is formal, but the real rigorous definition of this is psi tested against some function phi, against psi tested against some function psi. This is just phi tested against psi. So it's basically the same thing. So I mean, psi is not regular enough so that you can really define its value at a point x, but you can define this object, which would correspond to this integral of psi against phi. Okay. Of course, this expression does not make sense since psi of x is not a function, but it's a distribution, which exactly means that you can define these objects. Okay. And what's important for us is so what kind of regularity it has. So like I said, it's not a function, but you can still define its regularity in some Holder spaces. And the regularity of this white noise is that psi belongs to, if you look at a Holder space of dimension, just a little over minus d over 2. So let's say minus d over 2 minus. D is the dimension of the space, okay? So for instance, when d is equal to 1, then the white noise is just the time derivative of Brownian motion. So Brownian motion is not differentiable, so it's not a function, it's a distribution. And you get, so as we know, Brownian motion, almost surely. As we know, almost surely Brownian motion is Holder 1/2 minus, and so when you take the derivative, you lose 1 degree of regularity. You get minus 1/2 minus. So I will not define these negative Holder spaces, but I mean, for instance, in dimension 1, it's just basically something of regularity alpha minus 1 is going to be the derivative of something of Holder regularity alpha. Okay, so this is the regularity of white noise. One thing which, another way, we need some slightly different spaces to count regularity for these equations because you see here, this operator means that time and space should not be counted with the same homogeneity. So basically time should be counted as two space dimensions. So if you look at on RD plus 1, so all these equations we're going to be looking at are going to be this kind of heat equation plus some terms. So if you look on RD plus 1 and you have parabolic scaling, so that means that time is counted twice basically, then what you do is, so you have D, the space dimension, plus 1 which is counted twice, so minus D over 2 minus 1 minus. And let's write here parv to say that it's with the parabolic scaling. Okay, so this is the regularity of the white noise. So now, when we look at this equation, so we have the problem, of course, is going to be with the nonlinear term. Okay, so very similar to rough pass. The nonlinear term will not make sense a priori, because in general, when can we define two functions or two distributions? So we have something from C alpha times C beta, which let's say Fg maps to Fg. And this map makes sense if the two regularities add up to some string strictly positive. Okay, and let's say let's say that alpha is smaller than 0, beta is greater than 0, and what you get in the end is something which is in should be alpha plus beta. Right. No, wait. No, it's alpha. So these Holder spaces? Yeah. Well, maybe I'll speak about it later, maybe. So like I said, in dimension 1, you can just think of it as negative regularity means when you integrate enough, you get the typical Holder spaces. So when this is positive, it's just the standard Holder spaces. And when it's negative, at least in dimension 1, you can just see this as some derivatives of, so every time you differentiate, you subtract one regularity. But maybe I will give you, but maybe, yeah, or roughly, I will talk about this, but yeah. Okay, and so basically the point is that you can define, when you have elements, you can define multiplication only if the two regularities add up to something strictly positive. So again, in dimension 1, this is the same thing as Young integration, which we've already talked about, when you can define the integral of f dg when the regularity add up to something which is strictly greater than 1. So it's basically the same thing. It works also in multi-dimension. So in fact, you can even prove this theorem as a, say, corollary of the reconstruction theorem for Martin-Herer. So okay, so we have this, which works, and in general, when the sum is smaller or equal to 0, you cannot define the product of distributions in any meaningful way, in any continuous way. So what do we have here? So we have the KPZ equation. So what regularity do we expect? So at best, the best that we can hope for is that U is going to have the same regularity as the solution to the linear equation. Okay, this term is certainly not going to make things better. So what does that mean? So we have our white noise here. Okay, so here I need to precise that this is dimension 1. So space dimension 1 plus time. Okay. So then what is the regularity of psi? Let me write it like this. Psi we see here. So we have minus 1/2 minus 1. So it's minus 3/2 minus. Okay. Then basically, if you look at the solution to the linear equation, solution to the stochastic heat equation, this one, so the heat kernel improves regularity by 2. So psi is going to be in, right, psi has regularity 1/2 minus. Okay, you add 2 to this. Again, it's always in this with this parabolic scaling that we are counting here. Then you take one time derivative, you get minus 1/2 minus, and then wait, no, that's I think that's yeah, okay, so that's it. So I think okay, I think that's the right thing. Yes, okay. And well, clearly, when you so you add the regularities of this minus 1/2 plus minus 1/2, it's far from being something which is strictly positive. Okay, so we are very far from being able to make sense of this equation, of this term. We do not hope that it makes sense classically. Okay. So this is exactly the kind of problem that we have. So let me give a few more examples of equations which have the same feature. So another one would be the 543 equation, so the stochastic quantization equation. This time we're going to be in multi-dimension, so we have really the Laplacian.
The theory, you'd be able to say something higher dimensions?
For KPZ? No. I will explain why. In a few. So d=1 is really in d=2. It doesn't work anymore because of subcriticality, which I will explain. Soon, just in a few moments. Okay, so this equation where you would have U3 plus psi. So here this is again space-time white noise, and this time, so in dimension 1 it does make sense, but when you are in dimension 2 or 3 it does not make classical sense. But nevertheless the theory is going to work for this equation, so I can, if you want, you can try to count the regularities to see that you really have the same thing happening. And another equation, which is parabolic Anderson model generalized, would be, again, we always have this heat equation, and now we would take some function of u, so some nonlinear function of u, or linear even, times eta. So here eta is just space white noise, so we take something which does not depend on time. And here again, it's for dimension 2 or 3. Okay. So I will take this equation as a. So I will explain the solution theory. I will explain for this equation because it's the simplest one of the 3 equations. And there are also other equations, but these are the main examples. So all of these equations have important applications, right? So KPZ equation relates to motion of interfaces. This one has to do with, I guess, Euclidean quantum field theory. And this one, at least the parabolic Anderson model, which is when you have u here, it relates to some kind of limiting object for random walks in a random environment. So the random environment would be given by this.
These are all of the same type. That's on the left side of the parabolic.
Yes, exactly. Yeah, this theory, you really need some kind of regularizing property of, yeah, something like that. Yeah, it's very important. So it does not have to be the heat equation. You could have some other kind of hypoelliptic operator, but you need really some regularizing effect. Okay, so these equations do not make sense. This thing completely breaks down. Nevertheless, there is a little bit of hope, which I will explain now. Why? It's because of subcriticality. Which roughly means that at small scales, these equations, they rescale to the linear equation. So one way to see why this works, I mean, this kind of thing is, okay, this thing, it does not make sense a priori, this partial x u squared, but what if it did, okay? So what if we could somehow make sense of this thing? Then what can we say on the regularities of the term of the right-hand side? So we have, so for instance, for the KPZ equation, so the right-hand side, there are 2 terms. There is psi, okay, which has regularity minus 3/2, minus, and then the derivative of u squared. and this one. Okay, so what regularity is going to be? So in general, as I said, it does not make sense to multiply two things of negative regularity, but you have to trust me that if it did, so here you have something negative, if it did, the regularity should be basically the sum of the. So it does not exist, but if it did, this is the regularity that you expect it would have. Okay. So that means that this thing, if it exists, so it does not, at least until now, at this point it does not. But if it exists, you should expect it to have regularity. So the sum, so twice this thing, so minus one minus basically. And the important thing here is that this thing here is the regularity that you have here is strictly smaller than the regularity that you have here. So this sort of suggests that you can hope that at small scales, your U is going to look like the important equation at small scale is going to be the linear equation. Okay, and this is why this doesn't work in higher dimension. If you take d equal 2, this doesn't work. You don't have this anymore. Okay, and you can do the same similar. I mean, here it's basically the same computations. Here it's a bit different because it's not that you have a linear part plus, U has regularity 1/2, yes. No, I mean, it's just that you expect that at best it's going to be 1/2, okay? I mean, no, when I say 1/2, I refer to both x and t with the parabolic scaling, basically. So if you want, so it would mean 1/4 in t and 1/2 in x. No, it's not. It's definitely not obvious. But I mean, what we know is that the solution to the linear equation does have this regularity. Okay. Yes, and what we think is that this term is not going to make things better. So we think that at best it's going to have this kind of regularity. So at best, even at best, this thing does not make sense. And in fact, but this is in fact the true regularity of U. This is indeed this. Okay, so here we have this subcriticality means that at small scales, the linear equation is basically the rougher one. If it's the rougher term, is going to be the linear equation. So at small scale, it's the important part. Okay. Let's say is the dominant term, if you want. So then, what we hope to be able to do is So similar to what we do in rough path, where we say that controlled rough path, in fact, in controlled rough path, we have some function y, which is unknown, solution to some equation. And if we say that at small scales, it should be proportional to the driving rough path, then we can write some integrals, etc. So here you have something really similar that you hope that at small scales, U should be well described by let's say, so I had psi, the solution to the linear equation, plus possibly some linear functions of psi. Okay. Or if you want, what we are going to do, what we do in fact, this term we don't define it a priori for U, but if we know, so we define, if we can somehow, by some probabilistic argument, define the nonlinear term for psi. This, again, does not make sense classically, but nevertheless, there is some way to give some sense to it. I mean, in fact, it's not exactly this, but you have to renormalize. I will explain later. And then, once you have that, so you're not going to be able to just write U globally as some function of psi and some nonlinear terms, but at least locally you can do that. So then you solve for U in a space, sort of Taylor expansions with respect to basically these elements that you have defined. And then things are really nice. I mean, this function u, which has very bad regularity properties a priori. In fact, when you write it in this kind of Taylor expansion spaces, it's in fact infinitely smooth. You really have expansions at all orders, etc. OK, so let me make sure that I don't forget anything. OK, right. So this is a space of Taylor expansions. So yeah, we're going to have the usual polynomials, as in the usual Taylor expansions, plus some additional terms. So now let me make a diagram. So this is a diagram that you can find that Martin Heirer always does. OK, so I will explain all the terms. So let's say we have psi. We have omega, which is where the noise lives. So we are going to have several elements here. OK. So let me draw the diagram first. OK, so our noise lives in psi. Then what we're going to do is we have a lift map, which lifts the noise to a space of so-called models. So this map here is just a measurable map. A priori, it does not have any continuity properties. I mean, even defining it may be not so clear. So I will also, OK, so this one is a space of models, which, so if you know rough paths from the previous lectures, this corresponds to the space of rough paths, OK? Like in rough paths, when you lift your path to a rough path. The same thing happens here. And then, whenever you're going to be given an object here, you will be able to solve these equations in this space d gamma, which is the space essentially of a Taylor function with value in some Taylor expansions. Okay, so gamma here is the regularity of the function. So you have this map here, solution, let's say R for rough. This one is continuous. Okay. So you're given some noise, you can lift it, and then you can solve the equation in this space with values in the Taylor expansions. But that's not really the object that you're interested in. The object that you're interested in is the function, u, not its expansions. Okay? And to do that, you have some way to project down, which is called reconstruction. So in general, of course, alpha here is negative, so it's not really a function, it's a Schwartz distribution. But you have this reconstruction map, which is, again, continuous. Okay, and which in the end gives you the object that you want. And here you have this map, let's say solution S smooth. It's not always defined, so let me do it like this. This is, if you had a smooth noise here, you can always look at the same equation with a smooth noise. Then in that case, the solution is well defined. And this gives you this solution map. Okay? And what you want is that this diagram commutes so that at least the solution that you get for a smooth noise would coincide, I mean, with this, say, complicated procedure, would coincide with the solution that you would get by just solving the equation. Okay? Okay, so this is a diagram. There is one more thing which needs to be added to this diagram, is that in general, so when you look at in rough paths, things are sort of easier than they are here because in rough paths, let's say, okay, so let me erase here. So when we are in rough paths, there is this lift. It's not so hard to define in general. Okay, I mean you have to prove that it exists, but you just take modifications of your noise, and in the limit it converges. But here things are not going to work this way. So let's say, for instance, okay. So to say what I mean, so for in rough paths, let's say you have B epsilon modification of B. Then you look at the iterated integral, B tensor d B epsilon. And this one, when epsilon goes to 0, it does converge to something, okay? Which is in fact exactly the Stratonovich. So if you choose the right modification, it converges to the Stratonovich integral. But here, this is just not true, okay? you look at smooth psi here, psi epsilon. You have psi epsilon. You map to this pi epsilon, an element of this model space, but it does not converge when epsilon goes to 0. And you need to do something more. And what you need to do is renormalize this model, basically. So you have then an additional map. Okay. I don't know.
Despite this, you still get a universal solution.
Yes. So I will just explain a bit. So your model does not converge, but there is some renormalization procedure. So you have, let's say, R epsilon in this renormalization group, such that the renormalized model, so here is a map from the space of models to themselves, so that these models converge to something, okay? Of course, this limit is not unique because you can always, let's say, add a constant renormalization to have also convergence, but up to some factor in general, it's unique. Okay, and what happens when you renormalize the model? You don't keep the same equation, but you also act on this equation. So let me just put it here, right-hand side. So when you change the model, you also change the equation somehow. So similarly to what happens, so in rough pass, what we have in rough pass is you have a rough pass, and you can always add a perturbation at the area level, okay? So in rough pass, if you remember, I think Peter briefly talked about this at some point. You have x, and you map it to x tilde, which is just x plus, let's say, some kind of increment in the area. Then if you have dy equal v of y dx, no, when you solve with respect to the tilde, that gives you something. The difference with respect to the first one is just dy equal v of y dx, okay, the original one, plus you have some additional term, which basically involves the Lie brackets here, okay? And here then the drift is given by this. So this is the picture in rough pass, and here we have something quite similar, that when you when you change your model, you do change the equation. So for instance, okay, now let me give the typical thing that you obtain, and let me give a typical result. So for instance, the result for the KPZ equation that you can prove with the help of all this regularity structure construction. For the KPZ equation. So we have some modification of our white noise. So this is white noise convolved with some kernel, okay, rho rescaled at time epsilon. Then, for each of those, you can define the solution to the equation. You let u epsilon solve. So we have this u epsilon. So if you write just what you will have is this, okay? But in fact, as I explained, this will not converge. This would be what the solution that you obtain if you just keep the models and see what happens, but the models don't converge. This does not converge, but what converges is you need to change the equation a bit and in fact subtract some constant here. So the statement more precisely is there exists some sequence C epsilon such that if you let U be the solution to this, then U epsilon does converge to something, some function U. And the important thing, the very important thing here is that your constant here, that will depend on the modifier, but the terminal object, it will not, okay? Independent of the modifier. So it's really, the limit is really a universal object. Yeah, sure, it's a very explicit.
It's very explicit.
Yeah, it's completely explicit, yeah. So I'm not sure exactly what it is in this case, but it's really, yeah, it's very explicit. So yeah, maybe it's in 1/epsilon or something, I don't remember, but yeah. Okay, so this is really the kind of typical result that you get for these equations or for the other ones. So the renormalization does not have to be exactly of this form, it can take different shapes. But yeah, that's the kind of thing that you obtain. Okay, so I will start a bit with some kind of definitions and so on. I mean, with definitions. And like I said, I think we will more focus on this one for when I will give the examples for this equation. Okay. Sure.
So you said there are different models. So you must pass for this modification to work, so you need to approximate up to some level. Convergence of theoretic interval up to a fixed order. So is it the same kind of thing that is once you fix the model, you still need the convergence of a finite number of blocks?
Yeah, it's definitely something like that. It's very similar, yes. Just a finite number. No, it does not depend on the model. Yeah, I mean, it's just for this map. Yeah, it's just yeah. No. You in general you fix this index gamma here, which is the order up to which you do the expansion, and then you don't need to. You only need to check up to elements of this order. And the subcriticality exactly means that you only have a finite number of those. So it's really in practice, in theory, you only have. I mean, in practice also, you only have a finite number of those. But this finite number can be sometimes a bit high, which means that it can be quite technical. But yeah, in principle, it's just a finite procedure. Yeah. Okay, so now let me give a few definitions of let's try to define what are the objects here from this diagram. So there are basically 3 layers. The first one is what Martin Heller called the regularity structures. So now, okay, definitions. So this one is just the space of polynomials, basically. It corresponds to the space of polynomials. Abstract polynomials, if you want. I mean, it's better. Abstract polynomials. So these are not functions. They're just a basis. They're just the basis in which you want to write your expansions. Okay. So you have an index set A. Then you have the space in which your expansions take value, so which is graded by this index set. So it should be this one. It should be bounded from below and discrete, right? So in practice, like I said, we just do expansions up to some fixed order. So you can even take it finite here, and this also be a finite direct sum. It's not so important. And okay, so the expansions take values in this space. And then the other associated abstract object is you have G, the structure group, I think is the name. And it's basically the thing that you need to transport expansions from one point to another. Okay, and the only thing that you want is when you take gamma in G and you apply to some tau in T alpha, so with homogeneous of degree alpha, then what you get is tau plus some lower order terms. Okay. So I mean, lower order just means they are in, they take values in degrees strictly smaller than alpha. So I will give, okay, so now, I mean, let me give just this. So this is very an empty object, right? There is nothing there. I mean, there is not much content there. It's just some abstract space, vector space, finite dimensional vector space in practice. Gamma is just an element of G. Okay, so G, gamma. So all the elements of G, right? Okay, so they are transformation, linear transformations from T to T. Okay. So yeah, so I didn't say this. Indeed, it's good to know. So, G is a group of linear transformation of the expansion space. So what is the simplest example of this thing that you can take? Well, it's when you just want to do usual Taylor expansions. So really, you look at really polynomials. The polynomial regularity structure. Then what do you take? So your index set is just it's just n. You just polynomials graded according to their degree. Okay, and T is just the polynomials in certain number of variables. You may want to work with a certain number of variables. Okay, which is graded with respect to the degree. I mean, in practice, again, since we work with parabolic scaling, it's the degree, is a parabolic degree, so the time coordinate is going to be counted twice, but it's really, it's not so important. And then what is this thing here? So like I said, I mean, I will explain in a few minutes when I talk about the models, but this thing, the point is that they are used to transport an expansion at one base point to at another base point. So if you have a polynomial here, so G is basically is isomorphic to RD, and if you have some gamma which corresponds to some element of RD applied to some polynomial P, okay, an element of T, polynomial P of X, this is just the polynomial obtained by taking P of X plus H, okay? And you can see very clear, I mean, you see that you do have this property, right? If you expand P of X plus H, you get, I mean, okay, for some monomial of order K, P of, so if, for instance, X power K, if you take X plus H power K, you get X power K plus something which depends on H times some lower powers of X, okay? So this is really, you get this property here. Okay, I think I will define the structure for the parabolic Anderson model only later once I have a given definition of a model. Yes. Or maybe no. I mean, okay, let me do it now. Let me write down how we construct these structures for a given equation. So what is going to be the structure like for the generalized parabolic Anderson model equation? So first, let me rewrite the equation. So we had dt minus delta u is equal to f of u times, so let me call it psi. It's just space white noise, but let me call it psi. So the first thing that we do is we rewrite this in integral form. So modulo some impact of the initial condition, you can just write this as u is equal to the heat kernel convolved with f of u times psi. Okay. Plus some smooth term, I mean at least smooth for positive time, which is due to the initial condition. Okay, so and this k here is heat kernel. So what are we going to take in T? So first thing, so the first thing is that at least we want to be able to describe smooth functions. Okay, and to describe smooth functions, you need the polynomial structure. So you have the usual polynomial. The usual polynomial regularity structure is in practice always a subset of the one that you will consider. Okay. And now we want to, so we have these abstract polynomials, and we want to add more symbols with respect to which we take expansions. Okay. So the first thing to do is we want to add psi, something which corresponds to psi at least. Okay. Because okay. Now we want to have enough symbols to be able to describe the right-hand side of this equation. Okay. So we have psi. To that we will give the abstract symbol psi. Okay. So we are given some element of t, we must choose some regularity for this. And what is going to be? So what was the regularity? Okay, let's do it for d equal 2. So that means that space white noise, it has regularity a bit less than 1/2, okay? So this one, it has regularity minus 1 minus delta. Yeah, so I forgot to mention, but I will explain a bit later, but basically T alpha will correspond to elements which are of order alpha, which explode, which vanish at rate alpha near the point, or when alpha is negative, it's not exactly the same thing. Okay, so our psi is going to be given by this. So, or if you want, T minus 1 minus delta is just spanned by xi. Actually, let me do something to make things a bit clearer. I will write these abstract symbols, I will write them in some color. By discrete, I mean that on every interval, you only have a finite number of elements in A. But they don't have to be integers, okay? Yeah, I just okay, if you want, I don't mean at all that A should take values in some specific set, but you should have only a finite number of possible homogeneities. But they don't have, they certainly don't have to be integers. In fact, this is necessary that they're not. Okay, so let me see. Okay, so this seems like visible enough. All right, so we have this abstract symbol. Okay, now that means that, so what we want, if we had that, we would be able to solve this, okay? So now what we want is to be able to write, for each element that we're going to be in the right-hand side, we want to be able to give some expression which corresponds to the solution, to the heat kernel convolved with this thing, okay? Maybe let me do some kind of thing here. So here we would have some elements which appear in the right-hand side, and here we have elements with respect to the solution U. Okay. So first here we have the psi with regularity 1 minus 1 minus delta. Okay. And then we want to have some abstract symbol again, which represents the convolution of psi with the heat kernel. So we just define something, an abstract symbol, which we call IXI, which just means integration of psi. And what homogeneity do we want for this one? Well, basically, we want to take into account that the heat kernel will improve regularity by 2. So we add 2 to this one, okay? So it's going to be 1 minus delta. Okay, so that means that in the description of the solution U, you will have some, this factor is going to appear. We'll have something proportional to this, okay? So that means that then you want to be able to make sense of this, to have f of u in this thing, okay? So what f of u is going to be described as some kind of Taylor series, okay? Some kind of ak u power k. So that basically, we think of it as a polynomial with infinite degrees. That means that we want to be able to make sense of, so for you, you also, even here you also have the usual polynomials, and you have this term. So that means that in the right-hand side, you want to be able to make sense of all powers of things which will describe u multiplied by xi. So for instance, u is described by, you will have I of xi, so you also have I of xi times xi, okay? And also all powers, okay? So also I of xi power k times xi. And you also want, as I said, you already have the polynomial, so you also want all the polynomials times xi. And now, the important point of subcriticality is that when you count the regularities that you obtain here, you have something which are, at each time, when you come, so you do this procedure iteratively, you write down what you want for your right-hand side, then you basically look at their integrals, and then you come back, and you will only increase the regularity. So for instance, this term here, I of xi times xi, what do we have? So basically, here we have 1 minus delta. We multiply it by something minus 1 minus delta. So when we multiply, the way we count the homogeneity is by just adding, right? So, or at least
what's
I of psi. This is the abstract monomial, which corresponds to a convolution of psi with a heat kernel. Okay. This is just a symbol. This is just an element in the basis of the space in which we will do Taylor expansions. And right, yeah. And it should correspond to.
So why does it have regularity 1?
Because so psi has regularity minus 1 minus delta, and then you take convolution with heat kernel, so you improve regularity by 2, basically. So you add 2 to this. Okay. Right, and here we have minus 2 delta if you do the computation. So delta is basically anything which is very small. So here a little less than minus 1, and here a little less than 0. And in fact, so you see that if you fix a certain degree up to which you want to go, you will only have a finite number of terms with this procedure. So I don't continue, but this is how you do it. Right, so here I have basically defined this, and the structure group I don't define because it's a quite complicated definition, and I don't want to do that now. So I don't know, is it okay if we don't take a break, or? Yeah? It's okay, because I think since we started a bit late. Okay, so this is the regularity structure or the space of abstract polynomials. So at this point, it's completely empty. There is nothing, no data here, right? So we just have a set in which we do Taylor expansion. But now what we want to do is, to these abstract expansions, we want to link them to some concrete object, some functions. And this is done with a model, okay? And the objective is to go from abstract expansion to concrete element, function, or Schwarz distribution. Again, for those who know rough path, this corresponds to rough path, okay? To the rough path, to the reference rough path which you fix. So, okay, so what is the definition? A model, it's a pair pi and gamma. Right, so pi is a thing which, pi is a collection of map for each base point, pi x, and each of these maps, it goes from T to, say, the space of distribution. So let's call it, I don't know, S prime. Okay. So I don't use the usual D because we already have a D. So this is Schwarz distribution. Okay, so to an abstract element, you fix an abstract element in your monomials and a base point, and to that you get a concrete function. Okay. And so this is pi, and gamma. Gamma is just for each 2 base points, you have an element of the structure group. And this is just a way to transform the abstract expansions from one point to the other. So that means that, so let me give now a bit more precisely what we need. So as in for rough path, we have 2 kind of constraints. We have an algebraic constraint and an analytic constraint. So first, let me give the algebraic constraints, which are quite natural. Is that, okay, so this, it should transport expansions from base point to another. So you want some transitivity, okay? So you want that when you go from point Z to point Y, then from point Y to point X, this is the same thing as going directly from Z to Y, okay? And also, they should really correspond to transporting things. So you want that the way they interact with these models is via this equality. So you have let's say, some abstract element of T, which via pi y, you map it to some function on the whole space. And what you want to do is, if you wanted to compare it with something near pi some other point x, the way to obtain from pi x the same function is to do this transformation by gamma. Okay. So I mean, I will give some examples later so that it will be maybe a bit clearer. But these things are quite natural constraints. And now you have analytic constraints. So you cannot just choose your pi and your gamma, anything that you want. Okay, so the really important thing is pi, if you take some tau, okay, so I was supposed to do it in green. If you take some abstract monomial tau with homogeneity alpha, what you want, so via pi x you map it to some function, and what you want to, so this grading here should have the meaning that essentially then it corresponds to some function which vanish at rate alpha near x, okay? What you would want is something like pi x of tau. So this thing here, it's a function on the whole space. Evaluated at some point y, this should be smaller than x minus y power alpha. So this is something like that you want. In fact, it's not, you don't write it like this exactly because first, this does not make sense in general because this element is not really a function, it's just a distribution, okay? And yeah, even for negative alpha, it's not exactly what you want. So the way more precisely, the way you write it is if you test your distribution at base point x corresponding to these elements over the alpha with respect to this function phi x lambda, which I will explain what it means later, this should be of at most of order lambda power alpha. Okay, and phi x lambda is just, you have some function phi. So basically any function with compact support here, phi. And this one is obtained by rescaling. So you want to look at small scales near x, so you take something, so let's say here is lambda is going to be between 0 and 1. So you rescale your arguments to be of size lambda near x, right? So here is x. So this is phi x lambda. And also you also want actually to rescale in this direction to have to keep the L1 norm of phi that you had originally. So in fact here you take lambda power minus t. So this is really the important thing that abstract monomials of degree alpha via the models really corresponds to things of order alpha. So if you have something positive, or positive degree, it's very similar to this. So it's not exactly equivalent, but almost. And if you have negative degrees, then I mean these things blow up. It's just they don't blow up too fast. So you have some control. Okay. And there is also so up till now there was yeah. Okay. So I mean at this point there is no continuity of these functions pi's with respect to the base point, right? We just mean that they have this homogeneity, but you also need some additional constraints which I will not write down. So you have this thing here, and you have another one. It's some kind of Holder continuity of gamma. So if you want some, you want to know that when you look at something tau and you look at it translated, so it's from x to y, then this is smaller than something. Okay. Yeah. And all right. So, okay, let me see. Okay, so the space of models, Yeah, yeah.
And you construct a regularity structure adapted
To the equation. Yeah, yeah. Yes.
the
No. It's
related to that.
yeah. For each equation, you have a way to construct this vector space T in which you will take your expansions. And yeah, under this assumption of subcriticality, it will do the right thing. So it will. You can look only at a finite number of terms, and then you will solve in these spaces. Okay, so maybe let me give some examples so that it's a bit clearer. So first, for the polynomial regularity structure, well, it's quite simple. There's really only one thing to do. I mean, you don't have so much choice here. Okay, so, right, okay, let's do it. For the polynomial regularity structure, you have a canonical model. Which is just simply defined by, you have a point x, pi x, and some polynomial p. So what you obtain then is really a function, and evaluated at point y, well, this is just p of y minus x. Okay? So you look at this polynomial with respect to the base point x. And so this was the structure group, these translations. And again, this is simple, to go from point y to point x in a way which is compatible with this thing. Oh, okay, so I mean, just with this notation here, it just acts by translation, and I'm not sure exactly of the sign, but it's something like this gamma here at x minus y, or minus, I'm not sure exactly, but it's just, you can do the computation to find out. Okay, so here it's really very simple. You are given an abstract polynomial, and you look at the concrete function that it gives at the base point x. So now let's also try to see what we can do for this more complicated regularity structure. So as I mentioned in the beginning, we are not going to be able to directly give a meaning for the white noise, but at least if we have a smoothened version, so any smooth functions, in fact, we can define a model. So the graded structure is, so we take psi of regularity minus 1 minus delta, okay? Then we're going to be able to obtain some other functions, and the way you're going to count is when you have the product of a few terms, you just add the regularity. Psi is always going to have this regularity here, and whenever you integrate, you add 2. Yeah. Yes. Right. So whenever, so so for instance, t minus 1 minus delta, it's just the linear span of this thing here, so just a one-dimensional space given by this. Okay, and similar for t minus delta, minus 2 delta, it's given by span by this element, etc. So I don't. You cannot really give directly definition, but you just say that you add all these elements and then take with their homogeneities, and then you take linear combinations of those, and that's what you get. Okay, so there is no real direct definition of what is T alpha, but I mean you define your monomials, and then you define your T alphas just by being the vector spaces generated by those. Okay. Right, and if you have, let's call this smooth models for PAM. For the GPAM regularity structures. So let's say you fix some function psi, smooth function, on RD. And then, how do you define it? So you have this symbol psi. Okay, so first you have the polynomial. So for the polynomials, you just take, so I don't write it, but for the polynomial, you just take the canonical model. And then you need to make sense to these functions. So pi x of xi, in fact, this one, it will not depend on the base points, evaluated at point y, is just given by, this function xi at y. Okay, so here yes. Now, let's say that we want to make sense of this thing here. I x I xi evaluated at point y. Well, we wanted I of xi to correspond to the heat kernel convolved with xi. So this is k tensor xi at y. But in fact, this will not be enough, because what we want is something of order which vanishes at rate 1 minus delta around x, and this is just not true in general. Okay, so if you want to do that, you basically need, in general, you need to subtract some Taylor expansion, but here all that you need to do is so you want something, so you need to write the expansion up to order less than 1, so you just have k minus xi of x. And you can check that this really, I mean, in fact, for smooth xi, you really have something which is smooth. So in particular, this does vanish at order 1 your x, which is even better than you wanted here. Okay. And similarly, you can write the same thing. So for instance, as soon as, okay, so the difficulty in the end is to define multiplications, okay? But here, when we have smooth functions, you can just define the model applied to the product just as the products, okay? By x of xi times pi x of xi. This one here? This is just how you define it to be. So you want this to correspond to the product, some product, okay? So in general, it's going to be hard. I mean, in the limit, the product here will not make sense anymore. But as soon as you have a smooth noise, you can do it. Okay, so yeah, in the end, it's just what you want. And so on. So you can really do that iteratively, okay, with this kind of, as soon as you have an I, you define it with convolution, and a product, you just define it by the product. So this is the pi term here. For the gamma, again, I'm not going to explain what it is exactly, but for instance, you see that, so this one here, it does not depend on the base points, but for this one, for instance, if you want to transfer it from a point y to a point x, or let's say, to not confuse here, from a point z to a point x, then you will just need to subtract some constants which corresponds to this. So it's just I of xi. And again, I'm not sure exactly, but plus or minus this function at x minus this function at y times, so this is just a constant, so times the basis vector 1. No, it does not need to be an algebra, but so here I define this to be part of T. Okay. So it's a product of functions here. No, this is not in T alpha. This is an element. This is a function. This is in T alpha, but then via pi x, you map it to here. It's just smooth functions. Okay. So if you want, you can just write it as this is a function and evaluate it at point y. This is just given by the product of these two functions. Okay. In this case of smooth functions, and this is definitely not true in general. Okay, but here this holds. Yes, in general, you want to make sense of this in the limit for the white noise. Okay. Well, that's what I will explain, is that whenever you have a regularity structure and a model, you can define in some space, which I will talk about now, a solution, okay? And this map here, it's continuous in the model, Okay, and so here, if you look at a smoothened version of the white noise, you have a sequence of models that are defined this way. It does not converge, but you can make it converge somehow. And somehow, if you want, this will be that you will define here. You can, like I said, you don't. This really does not have to hold in general. You could also, for instance, add some function here, some constant here, and this is in fact what you need to do in practice. Okay. All right, and okay, and so here this is a smooth version of the model. Okay, so just one quick remark. So we have this space of models. It's a nonlinear space, right? Because you have these nonlinear constraints. But I mean, it's a subset of a more general vector space, and you can then define distance between models. Basically, yeah, if you have two models, you look at the bound that you get by taking pi minus the other one for this kind of thing. So you can define. So I didn't say this, but you can redefine easily distance on M, and it's let's say I don't know, Polish space. It's nonlinear, but it's a nice metric space. Although, yeah, no, the way it's like nice, it's not separable in general, but almost. So it's a metric space. Okay, so now I have defined this space here, and now let me explain what is this here. The space in which we want to solve the equation, in fact. So it is so-called model distributions. This is the third and last definition I need for this. So f is in d gamma. So f is in d gamma. That means that f is a function from Rd to t. Okay. So to each point we associate an expansion, an abstract expansion, and you need to have some. Okay. So something which is important. This vector space d gamma, it depends on some model. Let me just call the model pi, even though it also depends on gamma. And so these model distributions, they correspond to controlled rough path in rough path theory. So you fix a reference model here, and you want to have some expansion, some functions which to each point will associate an expansion in a way which has some regularity with respect to the model. So I will explain. So let me give the definition. It's quite simple. So from Rd to T, and such that, okay, so let's say first it should have finite L infinity norm, right? So this is an element in T. So you can have whatever norm you want on T. And then you have some kind of Holder condition. So what is this Holder condition? So you compare f evaluated at a point x, and you want to compare it with f evaluated at a point y, but you cannot do that directly. So first you need to basically transport this, let's say, expansion around the point y to an expansion near x. So the way to do that is with this structure group here. So this is why, in fact, f depends on the model. It's because gamma appears here. And then what you say, so you have this element of T, which is composed of elements of diverse homogeneities, right? Okay, so let's say sup over xy. Okay, so something which I forgot to say is that first, when we look at d gamma, so gamma is the level up to which we want to do the expansions. And so we only consider expansion up to degree strictly smaller than gamma, in fact. Okay. And then what we want to have, the exact condition, is that the component of degree beta, which I just write like this here, of this expansion, it should be of order x minus y power, gamma minus beta. So in fact, if you look at examples such as the polynomial, so maybe let's do quickly a quick example now, you see that this is a quite natural condition. Because this is just the simple definition of d gamma. So again, let me give a quick example. In fact, I mean, the starting point, let's say, is that if you look at the polynomial regularity structure with the canonical model, okay, of course, then d gamma exactly coincides with the usual C gamma spaces. Okay, it's if you want the map, or at least for say gamma, not an integer. The map goes in the way that here you have this function, and you map it to this, let's say, f, which at the point x is just given by the abstract Taylor expansion of f, of course. Okay, so f of x times 1 plus gradient of x times x, etc. Okay. So for instance, I mean, let's just do some simple example. So let's say gamma between 1 and 2. So d gamma for this polynomial regularity structures, f, so let's write it like this, f is in d gamma. That means that, so in that case, let's say we work in dimension 1, okay? In that case, what is t? Is just, you have constant vector 1 plus constant, so plus the monomial x, okay? So it's just two-dimensional space. And f is in d gamma, that means that first, at each point, you associate this expansion. So you have, let's say, f0 of x times 1 plus f1 of x times x. Okay, and the first thing that you see is that so you have these constraints here, and when you write them down, so at this point it's not clear what are f0 and f1, but in fact, as you see, you don't have so much freedom on how to choose them, because f1 really, you don't have any choice. It has to be the gradient of f0, or the derivative if you want. Just because you write this constraint, so let's say beta equals 0. What does that tell you? You have, so on level 1, f0 of x minus, so what is gamma, okay, let's do it like this, y of, so first of 1 is just equal to 1. Okay, the constant, it doesn't change when you change the base points. And of x, it's x plus, or I don't know, plus or minus, x minus y times 1. Okay, so first you look at level 0. So here, this gamma is just identity. So that means that f0 of x minus f0 of y. Again, beta equals 0, so it should be of order, wait, that seems wrong. No, okay, no, so sorry, that's not correct. So that means that when you take gamma, so let me ignore the xy of f of y, okay, from, let's say, y to x. This is just, so at level 1, you do get something, which you pick up from this. So you get 1 times f0 of y plus x minus y times f1 of x. Okay? And then on the second level, it doesn't change, so it's just f1 of y. So that means that when you look at the difference between f of y, this translated of f of y with f of x at the level 0, what you get is f0 of x minus f0 of y minus, so here we'll see what should be x, okay, yeah, looks good, minus f x minus y, no wait, f1 of x, so maybe let's do it like this, let's say f0 of y minus f0 of x minus y minus x times f1 of x. So this thing here, it should vanish at order strictly greater than 1, okay? So y minus x power, so it's gamma strictly greater than 1. And here you see immediately that what this implies is that f1 of x is just, I mean, this has to be the derivative of f0. Okay? And then when you look at the higher order, you just get immediately f1 of y minus f1 of x smaller than x minus y power gamma, minus 1. So what that means is that this constraint exactly means that this derivative here should be holder of constant gamma minus 1, which is, by definition, is the same as saying that f0 is in C gamma, okay? So just this is just a simple example to show that in the case of the polynomial regulatory structures, all these constraints here are quite natural because they really coincide with what you want from the definition of a C gamma space. So now, if you try to write this, if you write these constraints in general for this kind of model, it can be quite complicated. I mean, because this term here can be quickly quite messy. So, but nevertheless, I mean, this is still a nice definition. Okay. So now, what is something important? Not really, I mean, because, no, in fact, with respect to the usual rough path theory, it does not add anything, right? Because, so you have negative regularity, but this would just mean that instead of writing y as the integral of v of y dx, this would mean that you just look at y dot is equal to v of y times x dot. So if you want, this would be for rough path, you would look at the derivative instead of looking at the path. So x is Boolean motion now. So x dot is the white noise. Yeah. Well, in general, x is, let's say, in C alpha, with alpha between 0 and 1, okay? So that means that the derivative here would be between -1 and 0. So yeah, I mean, if you write it in this way, to go exactly from rough path to from this to usual rough path formalism, it's exactly what I said, which is that you have just replaced x by its derivative, but there is not more. I mean, you don't gain anything really. You get the same theory basically. But the important point is that you can do PDEs and not just ODEs. Okay, so we are doing quite well. I have already defined this. I have defined this. Now let me just talk, so not without defining it, I will talk quickly about this map R here, which is the reconstruction map. So we have this D gamma space, okay, which is a space of functions valued in these Taylor expansions. But what we want in the end, the objects that we are really interested in, are some functions, okay? Some function from Rd to R, for instance. So this is really the object that we are interested in. And what the reconstruction theorem tells you is that there is this map R, really, which goes from d gamma to a space of Schwarz distribution. So this is the reconstruction theorem. So there exists a map, say R, which goes from d gamma to some space of function. In fact, you can have some regularity alpha. So here alpha is just the smallest index in your regularity structure, such that, and so of course you don't want it to be anything, right? You want that this concrete function corresponds somehow to these expansions. And so what's the way to write it? So you have the reconstruction of some abstract expansion. And what you would want is that near the base point x, so you look at what would be given by the expansion near the base point x. So you have, sorry, let me do it like this. You have this expansion evaluated at the point x. So this is the abstract object. To this expansion, you can, via the model, give a concrete meaning. And what you want is that this reconstruction approximates well all of these objects near each base point x up to order gamma, basically. And I mean, okay, near x up to order gamma. And again, the concrete definition is given by what I had before, so Rf minus this thing by x f of x against, tested against some rescaled function phi x lambda is of order lambda per gamma. Okay. And so also very important, R is continuous. So it's a map which depends, it does not just depend on F because it also depends on the model. I mean, but so this is a bit of an abuse of notation because here each of the spaces d gamma will depend on the model, but this is a continuous map. And it's unique when gamma is greater than 0. Okay, so this is really important. It's that for these abstract Taylor expansions with some regularity, you associate really a function in a unique way, at least, when gamma, the regularity is positive. Okay, so I don't really have time to talk about the proof of this theorem. So yeah, let's, I mean, I will try to wrap things up a bit now. So just orally, the idea of this theorem is that, okay, maybe just a quick word. So for rough pass, what does it correspond to? It's basically the equivalent of this, of the rough integration map, okay? So in rough pass, what we have is we have a control pass y against a rough pass dx, and well, this is just defined as the limit for subdivision which converge to 0, which converge to, with step size converging to 0, of ys times some expansion, okay? And well, here basically you have to do similar thing. I mean, here you have to see this as this is x dot tested against the step function between s and t. I mean, same thing for here. And so without more explanation, Rf is similarly obtained as a limit basically of the models tested against, again, you have to have this kind of test functions with support which becomes smaller and smaller. And so basically testing against, you have to use a basis given by wavelet theory. I mean, wavelet basis. And you look at in the limit where step size goes to 0. So you cannot do something as simple as testing against these things here, because what you have here can be very rough, so you need to test it against something which are very regular. So you really need to use this, some results from a wavelet analysis, which tells you that, okay, you can find the test function with the right properties which are smooth enough. But okay, I mean, and yeah. So this is a bit confused, but this is again explaining maybe more clearly in Martin Herer's lecture notes. So now let me just quickly finish by mentioning the last two things that you have to do. Okay, so now we have defined this D-gamma space. And we can solve the equation in this D-gamma space, okay? So fixed point map. So we have this equation, U equal to K convolved with f of U times psi plus something, which is smooth, let's say. And now you write it, you want to write the as an equation in this D-gamma space. So you need to look at, basically you need to make sense of these terms here in this space of Taylor expansion. So let's say, let's call it U. I mean, I'm definitely not going to talk about this, but you can define some operator K, which basically does what K star here does. I mean, you just basically, now I'm just going to write everything in green, right? Because you need also to give meaning to a function f applied to an element of U, which is basically obtained by Taylor expansions. And here you have some multiplication times this symbol psi. And basically, the point is that now, this equation, you can prove that you need to change a bit the spaces in which you work. But there is this theorem which tells you that this equation is, let's say, locally Lipschitz. And you can solve it. There exists a solution. So at this point, everything is deterministic. So, I mean, as in the usual theory of ODEs, you don't know that you have global existence, but at least up to some explosion time. Victi, and a priori, you don't know that it's finite, but you know that you have a solution up to this explosion time. So this equation here, okay? Right, so something which I have not mentioned is that in the proof of this, you need to have some estimate on how the kernel, I mean, similarly to how you would write this down for a linear PDE, you need some kind of estimate, some kind of Schauder estimate. That basically, this thing here, it will, if you take something with some right-hand side, which is in some D gamma, this operator here will increase regularity by 2. And yeah, then you write your fixed point formulas and so on. Okay. So just what we have now, and again, and the map, which to the models, okay, and the map, which to the models map the solution, so which is in fact exactly this map here, SR. This map is continuous, okay? Which is very important. So the main, as in rough path theory, continuity is a very important property. Okay, so now we know that if we are given a model, we can solve this equation. Right, and I forgot to mention it, but I will just say it orally, that at least if you cannot just take, this equation is defined in a way that if you have a smooth model, then the solutions that you get in this way, you really have the commutativity of this diagram. So you solve this equation in ZD gamma for the smooth model, then you project it down via reconstruction. And what you get is the same thing as what you would obtain by solving directly the equation for the smooth and noise. Okay. So now what we want to, for each smoothened version of the noise, psi epsilon, we have a model pi epsilon, and we have this solution u epsilon in this D gamma space. So we know that here we have a continuous map. So all that we need to be able to, when epsilon goes to 0, this converge to psi, let's say the white noise. We would just want to know, does this thing here converge, okay? And the answer, as I mentioned in the beginning, unlike in rough path theory, you have a problem, which is that your models, they do not converge. But the good news, however, is that you can find some way to make them converge by some renormalization. So for instance, if we look, okay, let me look at, okay, so let's say we have now psi is a white noise. In general, I mean, the linear term is not a problem, okay? Psi epsilon, you take some modification of it. It does converge to psi in whatever space psi is in. So for instance, C minus 1 minus delta. This one is not the problem. But the problem is going to come here for, we had this first term I of psi times psi, which corresponds to convolution of psi epsilon times psi epsilon, say. And this thing here, when you epsilon goes to 0, it blows up, okay? It does not converge. However, it does not converge. However, the good news is that, for instance, you can do some computation, look at the Fourier decomposition of this thing, and you will see that the only problem is that the Fourier level 0, okay? So it converges to some infinite constant. So the level, the 0 level, so the level of the constant is blows up. But all the other levels, in fact, they behave nicely. They don't blow up, and they all converge. So that means, that, in fact, that you just need to subtract some constant C epsilon, which in practice, for instance, is just the expectation of this thing. And this thing here, it does converge to something. Converge to, I don't know, something.
There is a physical meaning to this renormalization. I mean, if you have cases in mind, does it mean something?
Yes. I'm not quite sure. I'm not sure. But I think that it's possible, at least in some cases, to have some physical. So I think Henrik Weber told me that. Yeah, but I don't know. I don't know about this thing. But yes. But so even if I can't tell you what the meaning is, it's still nevertheless clear that the object that you get is the right solution that you would want from the physical point of view. Okay, because it is known. Okay, so if you want, the way, I mean, you probably know this, but the way they were able to give solution to this before the work of Martin was to do this Kohlhoff transform, and then look at the multiplicative equation. Yes, and that they knew that this was the right solution. And if you want, this minus infinity then corresponds when you go back to some infinite Ito-Stratonovich correction term. Okay. All right, so that means that we have these models pi epsilon which do not converge. But you have pi epsilon, and to this one you will associate another model given by pi hat epsilon. And what that means is that, for instance, I have pi x of this I xi times psi. So as I said before this was just the product of these terms, but now it's just to this previous definition, you need to subtract some constant. You just subtract some constant. So times, let's say, no, okay, it's just some constant. So of course, this does not give the complete definition of pi hat because you also must define it on the other basis elements in a way that somehow keeps the structure. So it's not trivial to do, but nevertheless, I mean, it can be done. And then this pi hat epsilon, they converge to some limits pi to some limit pi. Okay. So you can prove then by using some bounds from some Gaussian bounds that you do have this convergence. I mean, it's some kind of Kolmogorov criterion that you need to use because convergence in these model spaces, it's some kind of convergence in some Holder spaces. Okay. So we know that we have convergence of this equation. So that means you have this U hat epsilon, which is the solution. I mean, okay, it's in fact given by R, the reconstruction of this fixed point solution to the fixed point map associated to this renormalized model. It will converge to something. And now what you want to know is, okay, so this, if you want to have the same kind of result that I mentioned in the beginning, you want to know what are these U hat epsilon, what do they correspond to? And then, I mean, it's not so hard. You just have to do this kind of a simple computation, which told you that you started with U epsilon solution to, so it corresponds to the, so okay, so U epsilon. Here it corresponds to this fixed point for the model pi epsilon. So that means we know that it's a solution to this parabolic Anderson model equation, f of U epsilon times psi. And now you want to know what is U hat epsilon. And in fact, so it's not so hard to see that this is going to be the solution to. So you have the same thing here, f of U hat epsilon. So here psi epsilon. And you subtract something. The subtraction here goes to something here, minus C epsilon. And here what you get is f prime of U epsilon, f of U epsilon. And yeah, I mean, so the final result that you get is that when epsilon goes to 0, when the modifications converge to white noise, you can fix some sequence C epsilon such that looking at the solution to this equation, they will converge to some object, which is in fact the object that you really are interested in, so the solution to this renormalized parabolic Anderson model equation. And I mean, this thing here, it's not so hard to have, okay? It's you just write this as it's just a Taylor expansion thing, okay? That's, for instance, okay, I won't do it, but as in rough path where you can not so difficultly interpret these corrections when you look at Taylor expansions, here it's basically something similar. Oh, I mean, okay, maybe I will do it, just so that you see where it comes from. So you have U, just right at the level of U epsilon. So, no. We have this abstract object. So it's, in fact, the value at some point x times, so it's the first level in the expansion. So it's just some constants. And then you have some other thing, which is, let's call it U1 of x times, so the first non-zero term in the expansion of U is going to be given by this thing. Okay, and then you see that so f of U epsilon by definition is just going to be f of U epsilon of x times 1 plus f of U epsilon of x f prime of utility. Okay, well, I mean, okay. Yeah, I think it would be a bit annoying if I have to do everything really, but just when you see that here this first non-zero term, a non-constant term in the expansion is going to be in Ixi. So that means that when you look at the equation where you multiply it by xi, you will get Ixi times xi, which exactly explain why, I mean, which is the one which you will normalize via the constant. So this is, okay, and I think I will stop now because I've gone on long enough. Thanks. Yeah. I mean, it's just classical solution anyway, because, yeah, if you want, but. Well, I mean, I'm not sure what you mean, because so the approximate solution is you replace white noise by a smooth approximation. Okay, so that anyway you do everything pathwise. Okay, you fix your omega, so it's always pathwise. You fix a smooth function which is obtained as a smooth inversion of your noise, but there is not much stochastic here going on. The only way, in fact, the only place where you need some stochastic results is when you're trying to look at the convergence of these models here. Okay. So this is a convergence, I don't know, in probability or something, but yeah. So yeah, it's very deterministic construction.
So you get the existence of solution. You get some estimates of the solution.
Well, what you get is since you don't get just this, you also get this. Okay, so you really get existence of a solution with a Taylor expansion associated to it. So that can allow you to get some estimates. So for instance, I think in the KPZ paper of Martin, there were some results of, for instance, what happens if you have two different initial conditions or something like that, right? Which was some results which were very difficult to obtain by the Kohlhoff transform, but with his construction, you could more easily obtain this kind of estimates. And also there was some kind of thing, some expansion on, yeah, so you.
It's a little local. Time up to time.
Yeah, yes, it's local, yeah. Yeah, but, well then, I'm not sure. So for instance, the way he did it for the KPZ equation, he said, we know that it exists by some other method, and since it coincides, then it must be, but okay, maybe because he didn't want to do any work, but for this parabolic Anderson model, I know that there is I'm not sure exactly how they do it, but at least in the paper of Gubinelli and co-authors, where they do things with a different technique but same equation, they are able to prove that the explosion time is infinity. I mean, that's you. And yeah, I think actually Martin has some results, maybe not of this equation, but another equation, where he proves existence of invariant measures, and so that means that implies in particular, I think that solutions exist for all time. Yeah. But I mean, directly from this construction here, you would not see it. I mean, it's very complicated nonlinear construction, so it's not clear how you would.
Thank you again.